This is another in our series of presentations in how hopefully we've achieved optimization of structures using both common sense and technology. And this one is a study of some work we've been doing in hyper-efficient floor slabs, which we've labelled Doing More with Less. Okay, the presentation touches on the objective of this work, the inspiration, the method we use, and finally, obviously, the results. Now, the objective was to design a reinforced concrete floor plate which is more efficient than the benchmark of a flat slab. And ultimately, the aim is to use less reinforcement, less concrete, the embodied carbon will be reduced, and then hopefully this technique could be extended to other types of floor structures, such as timber, leading to even lower embodied CO2 values. And the graph on the right shows the proportion of embodied energy in office buildings over years as legislation has come in. At the moment, embodied energy is quite a high, or projected to be quite a high proportion of the energy content of the building. So if we can reduce that, we're doing extremely well. The inspiration for this was originally Nervi's Gatti wall factory, which he labelled this as floor ribs which follow the isostatic lines or directions of principal moments in a flat slab, which is great, and I think it's along the lines of where we want to get to. We actually want to apply a more rigorous technological approach and see what result we get. So the method is to take a standard office floor grid. In this case, it's 9 by 7.5. Assume the floor slab is a plate of uniform material, and then obtain the principal stresses from our FE analysis. And you can see on the right the principal stresses in the 9 by 7.5 flat slab. And then we go into post-processing of the FE analysis model. Once we've done that, we export the principal stress vector field as a text file into Grasshopper, and the stress vector field in the flat slab is shown on the right. Then, once we've got this into Grasshopper, ribs are fitted to the principal stress field using a script which we've written, which sits within the program. And then once we've done that, the Grasshopper model is then exported into Rhino. So we've got a 3D model to manipulate the geometry. That 3D model is then exported into our analysis software. We run another FE analysis, and the results are on the right. The stress and deflections are outputted. And we then have an iterative loop, which we've scripted again within the FE model, which considers the utilization of all the rib elements, and then automatically changes their depth depending on the stress distribution. So it runs over quite a few cycles until it gets to what we think is the optimum distribution of depth throughout the floor plate, which looks as follows on the right. The right is a flatter image actually before iteration of the depth of the ribs, but it shows the pattern you get from matching a structure to the vector field. It's pretty similar to that obtained by Nervi. So we think we're very much on the right lines with this. And here's a 3D view. And the results, well, if you compare a 300 deep flat slab over the grid that we've chosen and the size of floor that we've chosen, this results in a volume of concrete of 182 meters cubed. It's a weight of reinforcement of just over 6,000 kilograms. And if you compare that to the new solution, we end up with a slightly deeper structure, 350 mil deep ribs, but they're quite narrow, and the slab is fairly shallow as well. But the volume of concrete is hugely reduced compared to just a uniform flat slab. In this case, it's 120 meters cubed of concrete. So something like a 33% reduction in concrete. The weight of reinforcement is marginally reduced, but pretty much the same. But the important thing here is to say, okay, well, 33% of concrete saved is actually equivalent to just over 0.2 tons per meter squared of embodied CO2. So that in itself is a very positive result. And that's it. And hopefully there'll be more. As I said, we're going to extend this into timber frame construction and maybe other forms of concrete structure. And if we do, we'll send out another presentation and keep you all updated. Okay, thank you very much.